Hello, we're going to begin a new chapter, Chapter 3. Chapter 3 deals with graphing rational functions. So, what makes a rational function is, well, we dealt with linear functions, right? Seen as mx plus b. But what if we had a fraction, thus making it rational? So, we have a fraction. What makes a rational function is the fact that we have a fraction. And we can have it set up as a polynomial divided by some other polynomial. Or not even that, we can just have a number over a variable, but making the entire function part of a fraction, it causes some new features in a graph that we never seen before. So in section 3.1, rational functions, we're going to talk about the domain and the asymptotes. Asymptotes are going to be a major key. We're going to talk about finding the domain, vertical asymptotes, behavior of vertical asymptotes, and end behavior, and we can also cover slant asymptotes. Rational functions. Over the last two chapters, the graphs of linear, quadratic, and polynomial functions have been studied. One characteristic all three of these functions have in common is that every linear, quadratic, and polynomial function has a domain of all real numbers. The result has every line, parabola, and polynomial graph as one continuous line or curve that has arrows on both ends, showing the graph continues forever to the left and to the right. In this chapter, we will study a function that does not necessarily have a domain of all real numbers. The result is a graph that is broken into several pieces. A rational function is a function written as a ratio or fraction involving two polynomials. Recall that linear and quadratic functions are technically polynomials, even though the term polynomial is a selection used while discussing them. The following is a small collection of examples of rational functions. So as we see, they're all written as a fraction. So let's know it's going to be a rational function. Domain of rational functions. From arithmetic, we must recall that division of 0 is undefined. So we can never have 0 in the denominator. That makes it undefined. For rational functions, this equates to the requirement that the denominator of any rational function is never allowed to be 0. This is the basis of finding the domain of rational functions. So for us, what's a domain? We want to think, what will make the denominator 0? Because if it makes it 0, then that's a case that's going to be a problem. And it's going to cause a break. Because we know for sure if it's ever 0, it makes it undefined. So how do we do that? We go ahead and we take the entire number on the bottom, or the entire polynomial, and set it equal to 0. With any rational function, we must make sure that the denominator is never 0. To determine the domain, we can solve the inequality. So we can set it equal to 0, or maybe even not 0, and we find what makes it true. So we go ahead and we add 4 to both sides, add 4, we get x squared equals negative, x squared equals, well, does not equal 4. We want to get rid of the square, so we take the square root and square root. So we get x equals plus or minus square root of 4. Remember, when we take the square root of both sides, we can't forget the plus or minus. The square root of 4 is 2. So our answer is telling us that x can never be 2, and x can never be negative 2. The description of domain as x not equal to plus or minus 2 depicts numbers to avoid. If we were to describe the domain as what numbers were allowed, the description would be, so let's talk about this notation. We have an interval notation, and that's how we want to see it. And sometimes it's hard to see what's going on, so draw a number line. So we're saying that, let's mark the numbers we're going to work with, 2 and -2. And we're saying that it can't be those numbers, right? In notation for number lines, we like to use an open circle to show that we have a hole in our argument. So what numbers work? The numbers that work are every number in between, every number bigger than 2, and every number smaller than 2. So to the negative infinity and to the positive infinity. So how we write this? We would say that it starts off, we read from left to right. We start off at negative infinity. And as we're looking through this, we see that we start at negative infinity. And infinities always start with parentheses, and we have to take a break at 2. So let's mark that we break at 2. We continue from -2, and then we take another break at +2. So -2 to +2. We go from 2 all the way to infinity. So then 2 to infinity. And this is our answer. But whenever we have a break in our parentheses, we write a U. This U means union. That symbol is pronounced union, and it means the sum or a collection of. So we're saying that all of those three parts together make up our answer. And that's how this answer came to be. So sometimes, even for me, it's really helpful to draw a number line just so we can see what we're working with. Example 2. What is the domain of g of x equals 3x minus 4 over 2x plus 1? Same idea. We want to take our denominator and set that equal to not 0. 2x plus 1 not equal to 0. We want to see what values will make it equal to 0, so we set it equal to not equal to 0. All right, we do some work. minus 1, we get 2x is not equal to -1. We want x by itself, so let's divide by 2. We get x is not equal to -1/2, right? So let's draw the number line so we can see what's going on. So we're just looking at the number -1/2, and it can't be that number, but it can be any number smaller than that, and it can be any number bigger than that. So let's write this as interval notation. So we start from the left. That would be negative infinity, and then we stop at -1/2. Infinities always use a parenthesis. We use a parenthesis for -1/2 because -1/2 is not included. It's just a stopping point. We have a break. We pick up at -1/2, and we go on for positive infinity. As is our answer is here. All right, I trust you can do this from here on. So do example 3. What's the domain of q of x? Example 4. What's the domain of x squared plus 3? As you can see, it yields an imaginary, and if we think of this as our x-axis, we never have imaginaries. So this will be the only case where we have all real numbers. Vertical asymptotes. The effect of a vertical restriction of rational functions will be the breaks in the graphs. A domain restriction is one value. A domain restriction of one value will result in two unconnected pieces of the graph. A domain restriction of two values will result in three unconnected pieces to the graph. This pattern will continue indefinitely, where for any number of domain restrictions, there will be one more than the number of unconnected pieces to the graph. It's probably easier to see when you graph it. At these breaks, the most typical behavior will be the graph getting close to a vertical line on each side, extending upward or downward but never touching the vertical line. This vertical line is called a vertical asymptote. So let's do these problems again. Example 1. What are the vertical asymptotes of f of x equals 1 x plus 1 over x squared plus minus 4? Just as before, to find the vertical asymptote, we'd set the denominator equal to 0. We found the answer is not 0, right? So our answer we have were -2 and +2. These cause these vertical lines, which are your vertical asymptote. So we have a vertical line at -2 and at +2. Because we have two vertical asymptotes, it causes our graph to have breaks, and thus it creates, think of it as in three parts. We have a part going on here to the left of the -2 asymptote. We have something different going on here in the middle between -2 and +2. And I have something entirely different going on here. So it split my graph into three pieces. We have our piece 1, our piece 2, and our piece 3. Now, again, example 2, we're going to take our denominator and set it equal to 0, but we already did that when we set it equal to not 0. You get that x is -1/2. And so this means I have a vertical asymptote at x equals -1/2. So let's find -1/2 in our number line, and that's our asymptote. That's your vertical asymptote. That's usually how we write it as short, VNA. And this vertical asymptote splits your graph into two pieces. The piece that's left of your vertical asymptote and the one that is right of your vertical asymptote. And we'll talk more about what to do with those two different pieces in the next section, but we'll see a glimpse of it here. For the denominator, this was a funny case. This one we got once we solved for 0. Oh, no, this wasn't the funny one. I think the next one's the funny one. We get x equals 3. So I have a vertical asymptote at 3, splitting my graph to that's left and right of my asymptote. In example 4, we set it equal to 0. And this produced eyes, right? Nowhere do we have eyes in our graph. So this one's all real numbers. There's no vertical asymptotes to consider. After these four examples, the domain restriction and the location of vertical asymptote for rational functions may seem to always be the same. There is one cause where it will not be true. Consider the example. So consider f of x equals 2x plus 6 over x squared minus 9, which by factoring can be written as, so for the beginning I can factor out a 2, and this one is just a differences of squares. So something funny happens here. Do we see how we can divide this? X plus 3 divided by x plus 3, they make 1. So our domain, the domain of f of x is negative infinity to -3 to 3, and 3 to infinity. Equivalently, x is equal to plus or minus 3. Notice that the factored version of the function has a common factor of x plus 3 in the numerator and denominator. Therefore, as long as x plus 3 does not equal 0, we can divide out the common factor, and we have this. So without the part that overlaps. This result in the function will have a vertical asymptote of x equals 3. The factor x plus 3 in the denominator of the original function, of the original version of the function restricts -3 from the domain, but because the factor x plus 3 can be divided out, the function will not have a vertical asymptote at x equals negative 3. Instead, the vertical asymptote of the graph of f of x will have a hole in the graph. So we're talking about these two pieces. So we have these denominators. We have x plus 3 and x minus 3. They produce x equals negative 3 and x equals 3. However, the one that comes from this plus 3, thus being the x equals negative 3, this will be shown in your domain, as we see here. You go through the process, we draw our number line, we get negative 3 and 3, and we do our domain as usual. So this is our domain answer. However, when we're talking about vertical asymptotes, that one in purple, or the one that's highlighted and scratched off because they technically divide to make one, thus canceling, that one will not reflect on our vertical asymptote. So our vertical asymptote will only be that positive one, the one that didn't get canceled off. X equals 3. So that's the only one that's our vertical asymptote. The other one will produce a hole. What we mean by hole is we'll graph it, but that single point, that singleton, we'll just draw an open circle to show that it's not part of our graph. Continuing on, if a rational function has a factorable numerator or denominators, it would be good practice to write the function in factored form to determine the function if the function has a vertical asymptote or holes in the graph that are restricted to domain values. Now let's talk about behavior on vertical asymptotes. After finding vertical asymptotes and knowing that a rational graph will never cross the vertical asymptote because they are correct domain restrictions, the next topic to discuss is the end behavior of every rational graph as it approaches a vertical asymptote. Consider the following function. So we have f of x equals 3 over x minus 1. So we find our vertical asymptote, we take x minus 1, we set it equal to 0, we get x equals 1. So we have our vertical asymptote. Now what's going on? What are we graphing? Well, let's pick some points that get close to 1. So we can pick 0, a half, 0.9, 0.99. So let's see what happens as we get close to the asymptote from the left. And then let's pick other points that are to the right of 1, such as 2 and 1.5 and 1.1. Numbers that get closer and closer to the asymptote but never cross it. We have the work done for you. To determine what the graph will do as it approaches the vertical asymptote, consider the following two tables. So we graph that 0, that a half, and 0.9 and 0.99. Numbers that get close to 1 from 2, 2, 1.5, 1.1, and 1.01. The first table has x values as approaches 1 from the left side. The second table has x values as values that are approaching 1 from the right side. Considering the proportion of the graph, continuing these points from f of x equals 3 over x minus 1, we see that the graph will be pointing nearly straight line up and down on the left side on the vertical asymptote and nearly straight up on the right side. So this is the end behavior. We see that it gets closer and closer to the asymptote but never touches. Same thing here. We see it gets closer and closer to the asymptote but never touches. That's a special feature on the vertical asymptote. We never cross it. We use this to guide us without having to plot too many points because we know we won't ever cross it. So I just emphasize that it would just go on forever and ever, never cross. This graph shows the end behavior that every rational function will have as it approaches a vertical asymptote. From other side of a vertical asymptote, the graph of a rational function will approach down to negative infinity or up to positive infinity. In other words, the curve gets closer to a vertical asymptote from either side of the graph. And behavior of rational functions. The final topic of discussion regarding the rational functions in this section is the end behavior of rational graphs. Recall that polynomial functions, the end behavior was controlled by the degree of the leading coefficient. Since rational functions are the ratio of two polynomial functions, the end behavior of rational functions is controlled by degrees of the leading coefficients of both numerator and denominator. The three cases we will study will have end behavior where the graph will approach the line. For two cases, the end behavior will be the graph that approaches the horizontal line called a horizontal asymptote. For the third case, the end behavior will be a graph that approaches a line with positive or negative slope called a slant asymptote. So there's more asymptotes to consider. Case 1. If the degree of the numerator is less than the degree of the denominator, the rational function will have end behavior approaching the horizontal asymptote y equals 0, the x-axis. So this is a type of horizontal asymptote. So this is horizontal asymptote case 1. If the degree of the numerator is less than that of the denominator, we're going to have a horizontal asymptote at 0, which is the x-axis. So if we see this one closely, our numerator has degree 1, and our denominator has degree 2. So this will be a case where our denominator is less than. So what is the end behavior? Well, it has a horizontal asymptote at y equals 0. The degree of the numerator is 1, and the degree of the denominator is 2. So the end behavior of the graph approaching y equals 0 or the x-axis, this is shown on the red line in the following graph. So this right here is our horizontal asymptote of y equals 0, which is the x-axis. Our second case for horizontal asymptote, there are three to consider, is if the degree of the numerator and denominator are the same, the rational function will have an end behavior approaching a horizontal asymptote of y equals a over b, where a and b are the leading coefficients of the numerator and denominator. So let's take a look at this next example. We see that both my numerator and denominator are of degree 1. So what would be my horizontal asymptote? Your horizontal asymptote will be made up of your leading coefficients. So that fraction that is made up by 3 over 2. The degree of the numerator and denominator are both 1. So the end behavior will be a graph approaching y equals 3 over 2. So 3 over 2 is the ratio of the leading coefficients of the numerator and denominator. 3 over 2 is 1.5, right? So we have a horizontal line at 1.5. Y equals 1.5. Or if you want to write it as a fraction, 3 over 2. All right, last case of a horizontal asymptote. So let's recall. We have one for when the numerator is less, so when the numerator is a smaller one. We have a case when they're same degree. So lastly, we're going to have a case when the numerator is greater. So a third case of horizontal asymptotes. If the degree of the numerator is greater than the degree of the denominator, the rational function will have an end behavior approaching a slant asymptote. Actually, I think we're going to include 4. Oh, we're missing one. I'll include a fourth one. Will be that of a slant asymptote. This will be when it's exactly just 1 degree greater. So we have to divide. We can use synthetic division. And our linear answer, so you ignore your remainder, our linear answer is our slat asymptote. So we'll have a slat asymptote of x plus 3, since that comes from 1x plus 3. Now the other case that we're missing is the possibility of not having an asymptote. So I'll write that in between here. There can be no horizontal asymptote, and that is when the degree of the numerator is opposite of the first rule. So the degree of the numerator is larger. If the degree of the numerator is larger. So that just means there's no horizontal asymptote, there's no horizontal line that I have to worry about not crossing. All right, section 3.1 got you ready to graph by talking about your domain and your borders, your asymptotes. We'll continue with section 3.2 in the next video. Thanks.